All right, today we're going to dive into the invisible world that powers, well, pretty much everything. Electric fields and electric field lines.
We've all been there, right? You're walking across a rug in your socks, you reach for a doorknob and zap, you get that little shock. It's a super common thing, but it's actually way more interesting than just a tiny jolt.
That little spark, that was you, having a very real, very personal encounter with an electric field. You've just literally felt one of the fundamental forces of nature. And we're going to break down exactly what it is and how it all works.
So here's our game plan. We'll start with the absolute basics, what electric charge even is. Then we'll get into the whole idea of this invisible force field. After that, we'll see how we can actually picture these things, learn a cool trick for charging objects without touching them, and finally, we'll get our hands dirty and do some real calculations.
Okay, so first things first. Before we can talk about a field, we have to understand what creates it. And it all boils down to one thing: electric charge.
The number one rule in all of electricity, the one you absolutely have to know, is right here. And it's beautifully simple. If charges are the same, like two positives, they push each other away. They repel. If they're different, a positive and a negative, they pull toward each other. They attract. Opposites attract and likes repel. That's it. This one idea drives everything else.
So where does this charge even come from? Well, it's baked into the fabric of the universe, into atoms. Every atom has positively charged protons and negatively charged electrons. And here's the key: things don't just magically become charged. An object gets a net charge because it either gains some extra electrons, making it negative, or it loses some electrons, leaving it positive. It's all about the movement of those tiny electrons.
And how do we measure this stuff? The standard unit is the coulomb, with a capital C. Now, the charge on a single electron or proton is unbelievably small. It's that tiny number you see there. To give you some perspective, you would need more than 6 quintillion electrons to add up to just a single coulomb of charge.
So if you have two charges, how does one know the other is there? They don't have eyes or anything? The answer is that every charge creates a zone of influence around itself, an invisible force field.
You know, the best way to wrap your head around this is to think about gravity. The Earth pulls on the moon, right? Even across hundreds of thousands of miles of empty space. It does that because it generates a gravitational field. Well, an electric charge does the exact same thing. It generates an electric field. It's its own personal area of influence.
So here's the official definition. An electric field is just a region of space where if you put another charge, it's going to feel a force, that push or that pull. It's the invisible arena where all the electrical action happens.
Okay, so if these fields are totally invisible, how in the world do we study them? Well, physicists came up with a really clever solution to visualize them. They invented the idea of electric field lines.
Here's the rule of the game. To figure out what a field looks like, we imagine we have a tiny, imaginary positive charge. We call it our test charge. The direction of the field line at any point is simply the direction our little positive explorer would get pushed. It's how we map out the invisible landscape of forces.
And this simple rule works perfectly. If you put our positive test charge near a bigger positive charge, it gets pushed away, right? So the field lines point outwards. If you put it near a negative charge, it gets pulled in, so the lines point inwards. Simple as that. And notice how the lines are bunched up closer to the charges? That's our visual cue that the field is strongest there.
Now this leads to a really important setup. If you take two metal plates, charge one positive and the other negative, and put them parallel to each other, you create this beautiful, perfect, uniform electric field in between. The lines are straight, they're evenly spaced, it's perfect. This means the force is the same everywhere between the plates. And this setup is a huge deal in electronics, particle accelerators, you name it.
So this idea of fields reaching out and affecting things leads to a really cool phenomenon. You can actually charge an object without ever physically touching it. It's a process called induction. Let's walk through this. Imagine you bring a negatively charged rod near a neutral metal ball. The rod's electric field pushes the free electrons in the ball to the far side. So now one side of the ball is positive and the other is negative. Now for the clever part. You connect the ball to the ground, literally a wire to the earth. Those repelled electrons now have an escape route, and they flow away. Then you cut the ground wire, and then you take the rod away. What's left? A ball that's missing electrons, giving it a net positive charge, and you never even touched it with the rod.
All right, the concepts are cool, visualizing is helpful, but now let's get down to business. Let's put these fields to work and actually calculate the forces involved. The main quantity we care about is the electric field strength, which we call E. It's just the force that would be felt per unit of charge. The formula is right there. E equals force divided by charge. It tells you how much oomph the field has at any given spot. The units, newtons per coulomb, make perfect sense. Force per charge. You'll also see it written as volts per meter.
Okay, time for a worked example. We've got that uniform field we talked about, we know how strong it is, and we're dropping a little positive charge right in the middle. The question is, what's the force it feels?
To solve this, we just need to rearrange our main formula. Force, F, is just charge Q times the field strength E. We're given the charge is 5 nanocoulombs, that's 5 times 10 to the minus 9 coulombs. We're given E, so all we have to do is plug and chug.
And there's our answer. The force is 1.0 times 10 to the negative 4 newtons. It's a tiny force, yeah? But it's a real, measurable force created entirely by that invisible field.
Let's try another one. This one adds an extra step. This time, we want to find the acceleration of a single electron in a field. This is going to be a two-part problem.
So, step 1 is just like before. Find the force with F equals QE. We use the fundamental charge of an electron for Q. That gives us a truly minuscule force. But we're not done. Now we have to pull out an old friend from physics class, Newton's second law, A equals F over m. We take the force we just found and divide it by the mass of an electron.
And just look at that number. The acceleration is almost 88 trillion meters per second squared. It's a mind-boggling number, and it perfectly shows just how powerful these electric fields are. Even a pretty weak field can make a tiny particle like an electron accelerate at an insane rate.
All right, for our final challenge, let's put the calculators down and just think conceptually. We've got a positive charge and a negative charge on a line. For each of those points, A, B, C, and D, what direction does the electric field point? Just remember our little positive test charge.
Okay, let's look at the answers based on our test charge rule. At point D, which is between the charges, our test charge is pushed to the right by the positive charge and also pulled to the right by the negative one. So the field points right, which is away from the positive charge. The same logic applies to point B, where the field also points right, towards the negative charge. Now at point C, just past the negative charge, the pull to the left from the nearby negative charge is stronger than the push from the faraway positive one, so the field points left, towards the negative charge. And finally, at point A, the table tells us the direction is towards the positive charge, which is the net result of the forces in this specific layer.
So we've seen that stationary charges create these amazing, powerful, invisible fields that can push and pull and accelerate things. But honestly, this is just the beginning. The really mind-bending, world-changing physics starts when you ask a simple question. What happens when these electric fields stop being static? What happens when they start to move and change and wiggle? Well, that is a story for another time. And it's a story that involves magnetism, light itself, and the very fabric of reality.